Next lesson in this unit is going to be rotation 3. In this lesson, we're going to look at two new topics dealing with rotation of objects, rotational kinetic energy and angular momentum. So first, rotational kinetic energy. So, we talked about before objects have kinetic energy due to their motion. So, we've done cases where we've had, a box that's sliding at some speed, right here has some mass, and that we'd say then the kinetic energy of that would be 1/2 mv squared, as our kinetic energy here. But that's kinetic energy that's in a linear direction. And so we called it kinetic energy here. We're actually going to rename it slightly. We're going to make it linear kinetic energy now because it deals with motion in a direction, because we also have, as we said, rotating objects. Rotating objects have kinetic energy due to their rotation. The faster they rotate, we'd expect they'd have a higher rotational kinetic energy. And so if we actually want to look at the equation itself, we've got it down here. Rotational kinetic energy is equal to 1/2 I omega squared. And so once again, you see this analog between these two. We have the 1/2 out here, just like we have the 1/2 in our linear kinetic energy. Instead of mass and linear kinetic energy, we have moment of inertia. And instead of velocity, we have angular velocity for rotational kinetic energy. So that's basically sort of how this equation works. So anything that's spinning, if we know how fast it's spinning, that's our omega, its rotational rate, or its angular velocity. The faster it spins, the higher the rotational kinetic energy. We know that the higher the moment of inertia. So if you have two objects that are spinning at the same rate that have the same value of omega, one has a high moment of inertia and one has a low moment of inertia, the one with a higher moment of inertia would have a higher rotational kinetic energy. Just like if you have two objects that are moving at the same speed, at the same velocity, the one with a higher mass would have the higher linear kinetic energy. So it works sort of the same way. So for rotational kinetic energy, let's work out an example of this. So a 5 kilogram rod of length 2.0 meters is spun around its center at a rate of 1.5 rotations a second. What's the rotational kinetic energy that it has? So we have some rod right here. And so we got some rod right here. We are going to spin this rod about its center. And so that's going to be our rotation axis. We know that the rod has a mass of 5 kilograms, 5.0 kg. It has a length of 2 meters. Okay, so its length there is going to be 2 meters. And so this is our setup here. We know, the question is, what's the rotational kinetic energy? Well, rotational kinetic energy, RKE, as we said, is going to be 1/2 I omega squared. So we need to figure out the the moment of inertia I, and we figure out the angular velocity omega. So for I, for a rod spun around its center, it tells us the moment of inertia is ml squared over 12. So let's put that in. So the mass of the rod is 5 kilograms. It's in the right unit, should be in kilograms, and it is in kilograms. The length of the rod is 2 meters. So we say 2 meters squared divided by 12 right here. And so we can do the math. 2 squared is 4, times 5 is 20. 20 divided by 12, let's see, is 1 2/3, so that'd be 1.667. 6.667. Remember, units of moment of inertia are kilogram meters squared. Okay, so we have the moment of inertia here. Next thing we need to figure out to find rotational kinetic energy is omega, the angular velocity, and so that's radians per second. So omega is radians per second. So how many radians does this go? And so it says 1.5 rotations. Well, rotation is 2 pi radians, so then our number of radians is going to be 1.5 times 2 pi, and then divided by the number of seconds here, and it says that's a second, so it's in 1 second right here. So once again, we can sort of do the math. 1.5 times 2 pi is 9.4278, and divided by 1 would be the same thing, because that's 1 second down there. So omega, as we said, is going to be 9.42478 radians per second. Okay, and so now we have to do is just plug it into our rotational kinetic energy equation. So we'll just continue that guy out over here. And so 1/2 moment of inertia, which we found to be 1.6667, okay, times the angular velocity, 9.42478 radians per second. and then quantity squared because of the fact that it's omega squared. And so we can once again just do the math on here and find our rotational kinetic energy. And so rotational kinetic energy in this case should be 74.022 joules will be our unit here, just the same way that other ones are. They're using these units of kilograms in here, meters for the length right here. So we have, as we said, kilogram meters per second, meters squared is the unit we want of moment of inertia. Using radians per second for omega gives us a unit of joules for rotational kinetic energy. Sig fig wise, we have 2 sig figs here, 2 sig figs here, 2 sig figs for our mass right here. So it'll be, we're doing multiplication by division, so this will be 2 overall. So rotational kinetic energy would equal 74 joules for this rotating rod. And so that would be how you'd go about finding a basic rotational kinetic energy equation. So looking at this in sort of the bigger picture, rotational kinetic energy is used in energy calculations the exact same way we've used linear kinetic energy, we've used gravitational potential energy, and we've used spring potential energy. We sum all of these up to find the total energy of the object. Now we just added something new that's on here. So rolling objects possess both linear kinetic energy and rotational kinetic energy. This is the fact that the rolling objects also have this rotational kinetic energy is the reason why, I don't know if you've noticed this, but as we've done problems, we have all sorts of inclines, and the natural thing you expect to put down inclines are things that roll, but we've never done rolling objects. We've always done boxes sliding down inclines and things that are sliding, not things that are rolling. And the reason why is because we'd have to consider this rotational kinetic energy if we were talking about rolling objects. And we've never discussed it until now. And so now we can start talking about that. So, if I have some object that's rolling at the top of the incline, starts off with gravitational potential energy. As it starts moving down the incline, by the time it, moves along later here, it's going to be moving in a direction, and so it's going to have linear kinetic energy that's going to be due to that amount here. It doesn't have a direction to it. It's a scalar, but it's due to that motion here. But then it's also going to be rotating as it goes around here, and due to the rotation, it's going to have rotational kinetic energy. And we have to sum those up to find our total energy. So let's just look at an example. Let's look at actually probably this one right here, where we have something going down an incline like this. So we have a solid sphere of mass 0.5 kilograms and radius 25 centimeters is rolled down a 3-meter high incline. So we have an incline. We're told that it's 3 meters is the height of the incline right here. We have our object, our sphere that's right up here. And so it says that the sphere has a radius right there of 25 centimeters. We want that in meters, so we'll put 0.25 meters is equal to radius. The mass of the object would be equal to, it says, is 0.5 kilograms. So 0.50 kilograms is the mass, so we have that. As it rolls down this incline, it's going to pick up not only linear velocity, but it's also going to pick up angular velocity, so it'll have linear kinetic energy and angular kinetic energy as it rolls. And the question is, how fast the sphere moving when it reaches the bottom? So, this is basically a work energy theory problem. So, with a work energy theorem, final energy is equal to the original energy plus the work. And so that's our general setup here. So let's look and see what we can figure out. At the beginning, it's going to be our original energy. Is that it's going to definitely have gravitational potential energy at that point. It's not moving yet, so it has no linear kinetic energy. It's not rotating yet, so it has no rotational kinetic energy. There are no springs involved, so that's not here. So really, it should only have gravitational potential energy at the beginning. At the end, when it gets to the bottom of the incline, it has, probably if we're doing this, we'd set our height to be at the bottom of the incline, so it would have no gravitational potential energy. It would have linear kinetic energy because it is moving when it gets to the bottom in a linear direction. It would have rotational kinetic energy because of the fact that it is rotating at the bottom. Once again, no springs involved, so we don't have to worry about that. So we sort of have an idea of what we're going to put in for our final energy. That'll be the linear kinetic and rotational kinetic. We have an idea on what we're going to put around for our original energy. That should be just gravitational potential. As this roll down, we're not worried about a frictional force or any other outside forces, which means that when we do this, we know that work is going to end up being 0 here, and so that our original and final energy should be the same. So let's see how this works out. So we said original energy, we said, is going to be equal to the gravitational potential it starts with, which is just going to be mgh. And so original energy here would be the mass of the object, which is 0.5 kilograms. So 0.5 kilograms. 0.50 technically, times g, which is 9.8, assuming this is on Earth, meters per second squared. The height on here is 3.0 meters. So I'll say it's 3 meters right here. And doing that gives us an original energy of 0.5 times 9.8 times 3, so that's 14.7 joules. So it starts off 14.7 joules. It should end with 14.7 joules as well, because of the fact there's no work being done on the system. So let's go ahead and let's take a look at this final energy. So the final energy we said is made up of linear kinetic energy and rotational kinetic energy. So linear kinetic energy is 1/2 mv squared plus the rotational kinetic energy, which is 1/2 I omega squared. So let's see what we know about this. So you know, m we've got, v we've got, I we don't have. So we're going to need to figure out what is the moment of inertia for this sphere. It tells us the equation for it, 2mr squared over 5. And so we find that moment of inertia, that should be 2/5, pull the 5 out there, times the mass, which is 0.5 kilograms, times the radius of the sphere, which is 0.25 meters, because I have to have that in meters squared. And so once again, we can just do the math on this. 2/5 times 0.5 is going to be 0.1 times 0.25 squared, that's 1/16. So 0.1 divided by 16, if I'm doing that in my head right, it's about 0.0125. 0.0125. Unit still kilogram meters squared for our units right there, because we put the mass in kilograms and the radius in meters. Good. So that's the right unit that we want right there. All right. So now that we know this, we can go ahead and start doing a little bit more. But actually, there's one other step we can do. We know we've got this omega that we're looking for, but really, we don't. If we plug in what we've got here, we'll have two variables. We'll have v and we'll have omega. We'd really rather just have one, because we can't solve this with two. And so there is another piece that we know, and we know that there's a relationship between the linear velocity and the angular velocity, and that's that the linear velocity is equal to omega r. And so, you know, let's go ahead and try to substitute for omega here so that we can solve this for v, because that's what we're looking for, how fast the sphere moving. That's a linear velocity. And so divide both sides here by r. And so that we get, r's cancel off, we get that omega is equal to v over r. And so we can go ahead and take that and plug that in for omega up here, and then let this simplify out a little bit. So let's plug this into our work energy theorem. So final energy equals original energy plus work. The work is 0, so final energy is what we're working out here. So final energy is going to be 1/2 mv squared. So that would be 1/2 the mass, which is, we said, 0.5 times the velocity squared. We don't know that. Plus the rotational kinetic energy, 1/2 I. Well, we already figured out I was 0.0125. 0.0125 times omega squared, but we're going to do that substitution because we found omega is v over r. So v, we don't know, over the radius, which we do, is 0.25 quantity squared. And so this should be equal to the original energy, which we found was 14.7 joules, plus the work, which is 0, and so it's just that. So now we have an equation we can solve. We just have one variable, v. And so let's go ahead and simplify it. 1/2 times 0.5 is just 0.25 v squared, plus, let's see, let's go to the math. 1/2 times 0.0125 divided by 0.25 squared, as we distribute that squared throughout that term. That's the v squared over 0.25. We do that, that comes out to be right at 0.1. So we get 0.1 times v squared equals 14.7. Just combine these two terms together. 0.25 plus 0.1 is 0.35. So 0.35 v squared equals 14.7 joules. Divide both sides by 0.35. 0.35 cancels out over here. V squared, let's see, 14.7 divided by 0.35 comes out to be 42. And then square root of both sides here. And so the velocity ends up being a 6. Let's see, round this to 2 sig figs? Yeah, 2 sig figs. So 6.5 meters per second. And so that would be the speed of the ball when it gets to the bottom, if it's rotating. So this is something to watch out for. Anytime you have a rotating object that is that's rolling, that you do have to consider both the rotational kinetic energy and the linear kinetic energy when you're working out problems. So Next thing we want to look at is angular momentum. So the angular momentum of an object is the angular analog to linear momentum. And just as the linear momentum of a system of objects is conserved if there's no outside force, the angular momentum of a system of objects is conserved if there is no outside torque, because torque is the analog with force. And so this is basically if you are this, you can sort of see this a little bit. If you ever sit on a stool, that's like a rotating stool, and you basically swing your arms and rotate your arms around, you'll notice that your bottom half of your body will rotate in the opposite direction. So you swing clockwise, then the bottom part of your body will swing counterclockwise. And this is because of the fact that the angular momentum is conserved, is that when you're starting off sitting there, you're not rotating at all, so you have the angular momentum of 0, but whenever you rotate the top part of your body say in a positive direction, then the bottom part of your body would have to rotate in the opposite direction so that the total angular momentum stays at 0. Because angular momentum is conserved. And so let's look once again a little more detail at this. So if we want to actually find angular momentum, the symbol for angular momentum is capital L. Once again, don't ask me why, but that's just what it is. So angular momentum is L. It's equal to I omega, so it's the moment of inertia times the angular momentum. And once again, this should look familiar because in the same way that angular momentum is L, linear momentum is P. P is equal to m times v. Sure enough, what's the analog of mass, moment of inertia? What's the analog of velocity? It's angular velocity omega, and so these two look very similar again. So L is the angular momentum, kilogram meter squared per second. I is the moment of inertia in kilogram meter squared, and omega is the angular velocity, and that's in radians per second. Forgot to put that in there. Okay. So just looking at this, we can sort of see a couple things that, once again, should make some common sense, is that the magnitude of the angular momentum increases with a larger moment of inertia. And so a really heavy object that takes a lot of torque to get spinning will continue to spin at that high torque. It's harder to stop it. It has a larger angular momentum in the same way that an object that's really heavy would have a larger linear momentum whenever it's traveling here. And the second is that the angular momentum increases the rotation rate. An object that's rotating faster will have a higher angular momentum. So those two things, once again, should be pretty straightforward in terms of how that applies here. The next thing we have to look at, though, is the direction, because angular momentum, like linear momentum, is a vector. Linear momentum, we said, is always in the same direction as the velocity vector. But when we start talking about things that rotate, it's a little more difficult to discuss an idea of what does it mean for something that's rotating to have a vector quantity, to have a direction to it. As we said, if it's a vector, it has both magnitude and direction. So to figure out the direction of the angular momentum, we use something that's called the right-hand rule. And we use the right-hand rule because it ends up following the same sort of structure that your right hand has. And so, if you look down in this picture, right down here, you can see we have sort of an image of a right hand. You can stick your hand in front of you and get the same thing. Like you're given the thumbs up sign and when you do that, if you were to basically reach your fingers out and curl your fingers around, if you hold your hand with your palm facing you and then curl your fingers, they'll curl towards you here. But if you notice is that they basically make out sort of a circle. They go in a certain direction. If you sort of take your hand with your palm facing and now point your thumb at you and then rotate your fingers, you'll notice your fingers actually rotate in a counterclockwise direction. And so that right there, that direction that it's going is basically the direction that's given by the right-hand rule, is that if the direction of motion follows your fingers, then the vector, that is your angular momentum vector, points in the direction your thumb does. And so you can see that down here. So we have this little disc that's illustrated down at the bottom. And so the direction of rotation in this case is going around that way. And so if you basically take your fingers and make your fingers curl around in the same direction that rotates, you'll notice your thumb points up. And so that's what it's showing here, that this vector, that is the angular momentum vector L, points up because that's the direction your thumb goes when your fingers rotate that direction. Now, note that if we did sort of this backwards, we had our object that's this way, but this time instead of rotating it the way it's shown in figure A down here, we're going to rotate it the opposite direction. And so if we rotate this the opposite direction as we go through, if you try to take your fingers here, you notice that, if you have your thumb pointing up and try to go this, your fingers go the wrong way. They go against the direction of motion. So instead, put your thumb down. And when your thumb is down, you'll notice that your fingers curl in the same direction as this arrow that we're showing here is pointing, the rotation that goes around there and goes around here, using the same type of illustration that we do in this picture right here. It's sort of the same disk, we're just sort of shifting it over. And so this is the right-hand rule. So overall, the right-hand rule says the direction of the angular momentum vector is at a right angle, so that's important here. You can see they show a right angle here. It's a right angle to the plane of rotation. So if the object's rotating in a certain plane, it's always at a right angle. And it's pointing in the direction that the thumb of your right hand would point if the fingers curl in the direction of rotation. So you curl your fingers in the direction of rotation, and then the thumb points in a direction that the angular momentum vector would go. And it's always at a right angle to that plane of rotation. And so this seems a little out there, but you'll see that this ends up making a big difference in terms of figuring out what happens with angular momentum and how it's conserved. So it has angular momentum has both magnitude, which we found from the last one, I times omega, and it has direction, which we use the right-hand rule to figure out. So because of this, it's important to remember that both the magnitude and the direction of the angular momentum are conserved if there's no net external torque. So since the magnitude is conserved, an increase in the moment of inertia of a rotating object will result in a decrease in angular velocity. And that should make sense because if L equals I omega, if we increase the moment of inertia, then it means we'd have to decrease the angular velocity if we want to keep the angular momentum the same. And of course, the opposite's also true, that if we decrease the moment of inertia, the angular momentum, or the angular velocity should increase. And once again, this is something that you've sort of seen here, is you ever watch figure skaters in the Olympics, they do their spins, is they start off with their arms out. And when their arms are out, they move their mass away from their rotation axis. They've increased their moment of inertia. And so they spin at a normal rate, but then they pull their arms in. And when they pull their arms in, that brings the mass towards them. That lowers their moment of inertia. And if their angular momentum is conserved, since there's no net torque on them, where no one's spinning them while they're doing this, so the angular momentum stays the same. And so because of the fact that their moment of inertia drops, their angular velocity has to increase. And so their rotation rate speeds up. And you can see that. They speed up very, very quickly as they go through here. And you can do this as well. If you take two sort of hand weights, like ones people use sort of just to work out their arms here, get in a rotating chair. And stretch your arms out, holding those hand weights as far out as you can, and then spin around, and then all of a sudden pull them in. And if you have a chair that doesn't have a lot of friction in it, and so it spins freely like this, you'll notice that you increase your velocity, your angular velocity. You spin a lot faster. And if you pull the arms, you stick your arms back out again, is that you slow down. You don't rotate as quickly. And so this is because the angular momentum of the system is conserved. And so that's something that you have to sort of deal with because of the fact that no net torque, the angular momentum is constant. The other piece is direction. So since the direction is conserved, a change in the orientation of a rotating part of an object without an external net torque will induce a change in the angular momentum of another part of the object. So that the total angular momentum is constant. So if you were to do something where, once again, let's say you sit down in a chair where it's not much friction, it rotates freely, and you were to take a bicycle wheel and spin that bicycle wheel, and get it going here. And so once it's going, you're sitting still in the chair, but the bicycle wheel is spinning. The system that you have here of you and the bicycle wheel and the chair would have a certain angular momentum. It's caused basically by finding the moment of inertia of the bicycle wheel times the angular velocity of the bicycle wheel plus the moment of inertia of the chair times the angular velocity of the chair, which would be 0 if you're not moving. But if you were to rotate that bicycle wheel, if you have it in your hands and let's say the bicycle wheel is sort of facing up and you rotate it sideways a little bit, the chair will start spinning. Because when you change that angular momentum, by changing the direction of the bicycle wheel spinning, then what ends up happening is the chair has to start spinning to counteract the change that you made in the angular momentum, because the angular momentum has to stay the same. And so if you change the direction of the angular momentum, well, it's going to affect the system. That's sort of the equivalent of doing one of these linear momentum problems where it all of a sudden starts going off in, it's an object moving in a straight line, but it hits something, and so it kicks off at an angle. And so now you have to worry about both x and y components of your linear momentum. You would also have to worry about x and y components of your angular momentum. If you have this bicycle wheel and it's, let's say it's rotating in this direction, this is the front up here, that's the back of the bicycle wheel, it's far away from you here. And so in that case, use your right-hand rule. Let's see, that's going to make this velocity vector go, the angular momentum vector go up. That's a right angle to that piece right there. Whereas we said this is the front right here, and that's the back. That's always the problem with drawing things in 2 dimensions. So in this case is that right now the angular velocity or the angular momentum vector is all in the y direction. But if I were to take this wheel and we were to rotate it, now it's around like this. Still, this is the front, and that's the back there. And look at the angular. We're still going to spin at the same rate. We have not changed the moment of inertia. We have not changed omega. It's still got the same rate of angular velocity here, but now your angular acceleration, your angular momentum is in this direction. You notice now we could say, instead of it all being in the y direction, we'd say now it has both a y and an x component. So we'd say it has an Lx and it has an Ly. And so there's been a change in Ly and there's been a change in Lx. And so that means that whatever was holding this spinning wheel right here would have to have the opposite. It would have to have, our other object would then see an Lx in this direction right here to counteract the change in angular momentum right here. And instead of a positive one that goes up, we'd see, actually in this case it would, the change would actually be, let's see, actually I think I got that backwards here. Let's see, so we'd have delta, we'd have to look at the changes. So the change in Lx, so Lx ended up in the positive direction, started off at 0. So Lx is 0 right here. So the change is positive. Okay, so yeah, so that change would be a positive direction right here. For Ly, however, Ly actually would be negative for this wheel because of the fact that originally all the angular momentum is in the positive direction. Afterwards, only a component of it because the total is right here. And so now we only have the y component here. So that means that the change in angular momentum in the y direction for a wheel would be negative. Okay, and so since it changes negative, that means that the other object, whatever it is, would have to have a positive change in its angular momentum. And so that would vary how the object rotated. It would make it probably want to turn itself. So whenever you have a system of objects, no net torque is that changing the direction of the angular momentum of one of the components will affect the direction of the angular momentum of the other components and change it. So let's work out some problems on this. So take the Earth. If the Earth's radius were to contract by 1%, how much longer or shorter would a day be? Because, if we're doing this without adding any no net torque, we're not making the Earth spin any faster or spin any slower by applying a force or applying a torque to it. It's just contracting. And so that means angular momentum is conserved. And so to find angular momentum, what we're going to want to do here is we're just going to set up our angular momentum equation. So, okay, let's look at the Earth to start with. Angular momentum is I omega. And so given the situation, we got to find the moment of inertia of the Earth. Moment of inertia of the Earth, since it is a solid sphere, 2m squared over 5. So our 2/5 times the mass of the Earth, which is 5.97 times 10 to the 24th kilograms, times omega, not times omega, times r squared. So the radius of the Earth is 6.37 times 10 to the 6th, quantity squared right there. And so we can do the math on this, and we're going to get a big number. So 2/5 times 5.97 to the 24th times 6.37 times 10 to the 6th squared, 9.6928, 6928 times 10 to the 37th power, maybe the largest number we've seen in this entire course. Unit still, so we have kilograms for the mass of the Earth, meters is the unit of the radius, so kilogram meters squared, which is the unit we want right here. All right, so we have that there. And then omega is, we said, radians per second. And so for that one, we'd say, okay, in a day, how many radians the Earth spins? Spins 2 pi radians because it goes through a full rotation. And the time in that's be 24 hours. And so we need that in seconds. So we take 24 hours times 60 minutes. So that gets us to 60 So a day, 24 hours times 60 minutes times 60 to get us to seconds. And so 2 pi divided by 24 divided by 60 divided by 60, 7.2722 times 10 to the negative fifth radians per second. So we've got those. We can find the angular momentum of the Earth to start with. So the current angular momentum of the Earth, what it is right now, would then be the product of these two, 9.6928 times 10 to the 37th times the angular velocity, yes, which is 7.2722 times 10 to the negative fifth radians per second. And so we get an initial angular momentum of the Earth of 7.0488 times 10 to the 33rd power. And so that's the angular momentum of the Earth to start with. Now, because of the fact there's no net torque on the Earth, we're just contracting the radius in a little bit, that angular momentum will remain constant. So that will also be our final angular momentum of the Earth. But in the second case is that the mass of the Earth stays the same, but the radius is different. And so, we're going to have to find a new angular momentum, a new moment of inertia. And so 2/5 times the mass of the Earth, which hasn't changed, 5.97 times 10 to the 24th, times the new radius of the Earth. Now it says it's contracted by 1%, which means the radius is 99% of what it was before. So we'll just say 0.99 times the existing radius, which is 6.37 times 10 to the 6th, and then square that. And so we do that, just do the math on it, comes out 9.5, almost on the dot's what I'm getting. So 9.500 times 10 to the 37th. So in looking at our angular momentum is that it's dropped a little bit. It's 9.69 times 10 to the 37th. Now it's 9.5. And so that makes sense. The Earth is contracted, so it means that the mass is not as spread out as it was before, and so that would lower the moment of inertia. And so let's go ahead and try to figure out the remainder of this, because we know that the angular velocity, or the angular momentum, is still saying the same, 7.0488. 7.048, that's an 8. I don't know why this thing's not showing up here, so 88. That is not another decimal right there, so we can get rid of that. 7.0488 times 10 to the 33rd. Wow. Should equal to, in this case, or in the new case, which is our 9.500 times 10 to the 37th times omega, which is what we're looking for here. All right, so we can divide both sides by 9.500 times 10 to the 37th, and so when we do that, I get an omega, which is equal to 7.41, 985 times 10 to the negative fifth. All right. So we have our omega here. So looking at the original omega, which was 7.27 times the negative fifth, now we get 7.41. Its angular velocity is a little higher than it was before, which means the Earth is spinning a little faster in this case, which makes sense. When we're talking about the figure skater, they pull their arms in, lower their moment of inertia, and that would increase their rotation rate. Same thing happens here. So we'd expect the day will be a little shorter than it was before. So we've already established now that the day is going to be shorter. Next question is how much shorter? Well, omega is radians per second. So the Earth is still spinning 2 pi in a day, but the time we don't know. And so that should be equal to our 7.41985 times 10 to the negative fifth radians per second. So multiply the t up, divide 2 pi by 7.41985, gives us a t of 84,680.7 seconds. We convert that to hours, so divide that by, divided by 3,600. Because that'll give us, divided by 60 will give us minutes, divided by another 60 gives us hours. And so t ends up being 23.52 hours. And so subtract that from 24.47758 hours, then times 6 to get minutes. That's 28.65 minutes. And so the day would be 28.65 minutes shorter if the Earth were to contract its radius by 1%, even a very small change in the Earth's radius makes a noticeable difference in the length of the day. And so sig fig wise, I guess all these are constants. So, or except for the 1%. So I guess maybe 30 minutes would be your best answer if you're doing this in minutes here. But that would be a way that we could sort of see that angular momentum is conserved. So let's take a look at just some more just general problems, not necessarily calculation problems, but let's look at how things change whenever we start changing angular momentum for an object there's no net torque. So here we have a helicopter. We have three different views of our helicopter from the side, from the top, from the front. And so let's say the helicopter's rotor blades spin counterclockwise when viewed from the top. And so we'll look at the middle picture, which from here. And so if they're counterclockwise, the rotor blades are going to spin in this direction right here. And so the question is, what happens to the body of the helicopter when the blades increase their speed? So first thing, let's look at the angular momentum of these rotational blades. And so, looking at the picture in the middle where we're looking at the helicopter from the top, we're going to apply our right-hand rule. And so when we apply our right-hand rule, we take our right hand, we wrap our fingers and curl them in the direction that the rotor blade is turning. And so in that case, when I do that, my thumb points out towards me. It points out of the screen right here. And so the way that, just as a note here, I don't know if we mentioned this before, but the way you actually show vectors that point out or in is a vector that points out, you do with a circle with a dot in the middle, like you're seeing like the point of the arrow. If it were going in, then what you do is you would do a little X through it, like you're seeing the tail feathers. That would be a vector that's going into the screen, versus this would be a vector that goes out of the screen right there. And so in this case is that this angular velocity vector, because the fact we use our right-hand rule, for the rotating rotor blades would point up towards us in the middle picture. If we were looking at this in the top picture, where we're looking at the aircraft from the helicopter from the side, the angular velocity or the angular momentum would be going that way, because in this case that the rotor blade spinning would